So let me start by reviewing a little bit from the last lecture. We were talking about the Gaussian ensembles, which was a model for many universes containing gravitational waves. And this model, as I explained, is motivated by things like the central limit theorem. If you have many, many weak sources all adding together incoherently, this will give rise to a Gaussian process. Although it's not clear that this describes, for example, the sources that are relevant for PTAs. And in the Gaussian ensemble, the amplitude of gravitational waves h at frequency f propagating in direction omega hat is characterized by, if you average over all of the universes in the ensemble, the expected value is 0, and the expected value of the correlation or covariance has the property that there's no correlation between the different polarizations. There's no correlation between the different frequencies appropriate for a stationary and time process. There's no correlation between the different directions appropriate if the radiators are all independent of one another. And finally, there's a function h of f, which characterizes the distribution of energy among different frequencies. And you saw that because I derived a formula for omega of f, this dimensionless spectral function, in terms of h. And we computed some stuff, for example. I did a computation of what's the expected value of the squared strain, this measure of squared strain. And we got 16 pi times the integral of h of f df. When I write an integral like that without any limits, it means minus infinity to infinity. So if I wanted to write this in terms of a single-sided power spectrum, you'd put in a factor of 2. And then the last thing we did was I computed the expected value for the correlation between the redshift of two pulsars, which I called A and B. And you remember my warning that in this expression here, A and B are indices that mean x, y, and z, or 1, 2, and 3, whereas now these are pulsars. And the answer looked like the following to this calculation. First of all, there was a term that looked up to a factor of a quarter like this squared strain. So that was just a measure of what's the amplitude, the average amplitude of the gravitational waves. Then there was a very interesting factor of 1 plus delta AB. That arose because if you're looking at two pulsars that are different, then at least in the Gaussian ensemble, assuming that the coherence length is shorter than the average distance between pulsars, that's the mathematical thing that let me drop the two terms that I dropped, sorry, the three terms that I dropped. Then the pulsar terms are uncorrelated. You get the 1. But if you're looking at the correlation between the redshift of a pulsar and itself, then the pulsar term also correlates, and that doubles the amount of correlation on the average. So that was the factor of 1 plus delta AB. And finally, there was something that I wrote as mu mu of gamma AB. And that was the Hellings-Downs function. I think I'm going to write it over here on the right. I'm going to just glance at my notes and make sure I didn't drop any factors of 2 or 4 here. I think that agrees with what I wrote down. Yeah, it looks good. Okay. And this function is defined in the following way. I'll put the gamma dependence a bit differently here. So it's an average over directions of gravitational wave propagation of a sum over polarizations of the response of the first pulsar. I'm going to call it now p hat a. Remember that a there does not mean the x, y, or z index. It just means which vector is that. And then there was the response. That was multiplied by the response of the second pulsar. And this is all summed over polarizations. And this function is called the Hellings-Downs curve. I'm going to show it to you in a minute. And it depends only on the angle between pulsars A and B. So here, gamma AB, quantity that appears there, is the angle PA to PB. Cosine gamma is p hat A dot p hat B. Okay, so I think that's where we were last time. And I want to start off today by just writing down this integral explicitly. I'm not going to evaluate it, but it's one of the problems that I've put on my list of problems. And I just thought I would actually write it down. It just takes 5 minutes, but and it's kind of a mess. But at least, I don't know, it's something explicit and concrete, so why not? By the way, you could also, if you wanted to, replace this sum over polarizations. You could take away the sum, take away the a's from here and here, and just put a complex conjugate on the second one. That would also be correct. And in case you're wondering, Javier, about the imaginary part of that, it integrates to 0 because one term is symmetric under omega goes to I minus omega. The other term changes sign. So the imaginary parts that might appear that you might worry about, if you did what I suggested, if you crossed off this sum, you crossed off the a's and you complex conjugated, that integrates to 0. Okay, so let's actually just write down this integral just kind of for completeness. And to help me a little bit in this, I'm just going to remind myself that m hat was sine phi x hat minus cosine phi y hat, and that n hat was cos phi x, cos phi, this would be cos theta x hat plus sine phi cos theta y hat minus sine theta. That will be helpful for me to get the algebra right. So how are we going to do this? Let's do the following. I told you that this depends only on the angle between the two pulsars, and you can actually see why that's true. You sort of just change your integration over omega. You can rotate that if you like. And you can imagine rotating here your integration directions until, for example, the first pulsar, PA here, its direction vector is just z hat. And the second vector, PB, let's let that be cos gamma z hat plus sine gamma x hat. So here's now just explicitly two vectors. And so now I'm going to just compute here what are FA and FA of the first and second arguments. So let's see. You recall the definition. I guess I'll make use of this. FA is 1/2 p hat A, p hat B times the polarization vector, tensor, pardon me, divided by 1 plus omega hat dot p hat. And by the way, here the A and B now are back to being x, y, and z indices. I really should have been more consistent about my notation, but so let's compute, first of all, f plus of omega and p hat a. So as you recall, E plus is m hat minus n hat, and then in the denominator we have 1 plus omega hat dot p. So I remember that the z component of omega is just cos theta. So the denominator here is just going to be 1 plus cos theta. What's the numerator? So for the numerator, I'm going to dot this p, z hat, twice into E plus. E plus, you remember, is m hat minus n hat. And I know that z dot m hat is 0. Whereas z hat dot n hat is minus sine theta. So the denominator here is going to be, I was going to write minus n hat dot z hat squared, but I think I'm just going to write minus sine squared theta. Okay. And you recall, this sort of satisfies the thing that we figured out also the last time, that actually this is non-singular. The minus sine squared theta here, that's cos squared minus 1, which is cos minus 1 times cos plus 1. So I guess that would make this 1/2 cos theta minus 1. Can I have a thumbs up from somebody who's checking my algebra? Okay, thank you. All right, what about f cross? Can anybody do that in their head? Remember what E cross was. The cross polarization tensor was m hat n hat plus n hat m hat. Anybody do that in their head? So you're going to have z hat dot m hat times z hat dot n hat plus the other way around. How come?
Because m hat does not have any z.
Exactly. It's going to give 0. Thank you. Good. F cross of omega hat p hat at a is 0, which is great because now we've done one of these two terms, that one. For the other one, we only need to evaluate the plus component because the cross component vanishes. A couple of people look confused right now. Is somebody confused? A question? Okay. I'm sorry, I'm asking you to remember the definitions of E plus and E cross here. Okay, so now let's do the other one. This is going to be a little bit nastier. So let's see, let's do the denominator first. This thing. So we need now 1 plus omega hat dotted into this. So that's going to give me a 1 plus cos gamma cos theta, because I remember the z hat component of omega is cos theta. And then there's going to be plus a sine gamma. And the x hat component is going to be cos phi sine theta. So there's the denominator of f. Ooh, this is a mistake. I should not have written f cross here. I should have written f plus. Pardon me. Okay. Remember what we're doing now. We're calculating the second term in this sum. We've calculated this one. Now we're doing that one. Okay, what about the numerator? So the numerator, we need to dot this into m hat minus n hat. So let's do that. So when we dot pb here into m hat, I'd written it down to help me. you can see that the z hat component here isn't going to matter, but there's going to be a sine gamma times a sine phi, and that's squared. So that's p hat dot m hat squared. Then we're going to subtract p hat dotted into n hat squared. That's going to be a slightly nastier expression, but let's just do it. So the x hat component here is going to give us a sine gamma cos phi cos theta. And the x, that was the x hat component, and the z hat component is going to give us a cos gamma sine theta. Squared. Okay. It's not pretty. You can make that look slightly nicer, but I'm not going to try. So at the end of the day, this function, as a function of gamma, is the following. I'm just reading now from this equation, substituting in. It's 1 over 4 pi. There's an integral d phi from 0 to 2 pi. There's an integral sine theta d theta from 0 to pi. There's an algebra mistake here. Anybody spot it? Minus? No, I don't think there's a minus sign missing. The denominator is correct. That's 1 plus omega hat dot p hat. And the numerator is p hat dot m hat squared minus p hat dot n hat squared. So it's not a sign mistake. There you go. I dropped my half. Okay. All right. So that's the integral d omega. And now the sum over a here is just going to be f plus times f plus. So we're going to have two factors of half. So I guess I'll change the 4 pi here to a 16 pi. And I apologize to those of you who are taking notes. But hopefully you're actually working this out for yourself. And then there's going to be a 1/2 cos theta minus 1. Sorry, there's going to be a cos theta minus 1. And finally, there's going to be this mess, which I will just write on the second line here. Why not? Sine gamma sine phi squared minus sine gamma cos phi cos theta minus cos gamma sine theta squared. Okay, so here we have a function of the angle between the directions to pulsars. If you read the original Hellings-Downs paper, they write down this integral, and then they just give the answer. And at the very end of the paper, they acknowledge somebody for helping them use maxima. That was a symbolic manipulation program at the time for doing this integral. And I have to confess, when I started working on this topic, I got to that integral and I thought, this can't be so hard to evaluate. And I spent several days trying to find a clever trick to evaluate it and couldn't find one. And then something came along and distracted me. And I wanted to do some other calculations involving this. Eventually, I got back to it. So one way you can do that integral is by contour integration. And I've actually assigned that as a problem. If I was teaching a longer course, I'd actually do this integral. It would take a couple of lectures. You can also just do it numerically if you're interested. And so for those of you who enjoy writing code, this is a few dozen lines of code. And you can do Monte Carlo, pick points on the sphere at random. You can make a grid that's uniform in phi and uniform in cos theta. Anyway, if you're interested in this topic, you should do that. And I think if you give this integral to Maxima, for example, or sorry, to Mathematica or to Maple, I don't think it can do it. Okay, so before I move on, I just want to ask if there's any questions about this or if there's any mistakes before I shove the boards up to the top and they're lost to me forever.
Solving the integral using that expression in spherical harmonic decomposition for f.
That's coming next.
Wouldn't that like reduce to some to that theory?
Absolutely. I'm actually going to do that. That's actually the next topic. Okay. The thing is, I didn't prove to you that f had that form that I wrote down. If I'd proved that, then I'd say, okay, I've really done my job, but I'm asking you to take that at face value. Okay. All right. I don't hear any objections to the algebra, so these boards go up to the top. And I'm going to leave them there until the end of the lecture. Okay. So let me just show you what the curve looks like. Oh, gosh. And I was going to write something down there. Okay. I was going to write down the answer, of course, after you do this integral. So when you do this integral, you get 1/3 plus 1/12 cos gamma minus 1 plus 1/2 1 minus cos gamma times the natural log of 1 minus cos gamma over 2. A very nicely behaved function. When gamma goes to 0, that's the angle between the directions of the pulsars being 0, the cos gamma minus 1 vanishes, so does the x log x, and you're just left with 1/3. And the curve looks like the following. It's, I've shot myself in the foot here. I've normalized. This curve is normalized differently, so maybe it's a good time to say. It's often the case in the literature that people use a slightly different definition. So maybe I just say, warning, in Italian, nota bene, that often the literature multiplies by 3/2. And so you can multiply that formula by 3/2, which means that the value at gamma equals 0 is not 1/3 like it is there, it's 1/2. And that's what I've plotted here. The reason that people do this is kind of obvious if you look at that 1 plus delta AB, because they want to interpret this as a correlation. And the idea is that with the normalization with this extra factor of 3/2, then the correlation of a pulsar with itself, it's the 1 plus delta AB, that's 2, times the 1/2, that's 1. So if you want to interpret this as a correlation, it's very convenient to insert this extra factor. It doesn't affect any of the equations. You can write the equations in terms of either quantity, but okay. So here we go. Here, of course, there's no factor of 1 plus delta AB, right? So this is two pulsars that are very close together on the sky, but not identical. They're more than one gravitational wavelength apart from each other. And these are quite correlated. Now, as you swing down and you're separated by around 50 degrees, on the average, pulsars are uncorrelated. I say on the average because this ensemble average is really doing a lot of averaging. So this does not mean that any two pulsars that are close by in the sky are necessarily going to be correlated. They might not. It depends upon what the actual sources are. The difference between the fact that the expected value of z was 0, even though in no universe was it actually equal to 0. Same thing applies here. This is an expected value, not what we would actually find. Okay, so around 50 degrees, there's no correlation. Around, let's say, 80 degrees, they're actually anti-correlated. So a pulsar there and a pulsar, 80 degrees, a pulsar there on the average are going to actually be anti-correlated with one another. And as we swing all the way around to 180 degrees apart, we're back to correlation again. So this curve is important because, in fact, the detection of this pattern of correlation, it's equivalent to the chirp waveform, which told us that with LIGO we'd actually seen gravitational waves. The detection of this curve is the smoking gun that indicates that gravitational waves have been found, that they're the cause of correlations between pulsar timing arrival glitches. And I just thought I'd quote something. This is from the International Pulsar Timing Array Checklist for the detection of nanohertz gravitational waves. Quote, to demonstrate that gravitational waves are creating some of the noise in the pulsar timing data sets, observations must exhibit this curve. So that's why it's kind of of fundamental importance. Also important for data analysis. Okay, so let me move on to the question that was just asked. And I want to actually show you a different derivation of this curve. This is one where if you accept the formula, I can actually do the calculation on the board. And it gives some insight as well. So I'm just going to label this harmonic analysis. And this comes down to the formula which I wrote down, I think, a lecture ago. And I'll write it down again. It's a very pretty formula. This is now the complex response. So this is F plus I F cross in the notation I've got up there. For gravitational wave going in a direction omega and a pulsar in direction p. And the formula is the following. This quantity can be written as a sum, L starting at 2 and going to infinity, and m going from minus L to L, of a set of coefficients, which I'll call AL. I'll define those in a second. And by the way, the formula that I wrote down 1 or 2 lectures ago, I put a question mark next to it. There was a mistake in that formula. I'll get it right this time. Then we've got the dependence on the gravitational wave direction. That's spin weight 2 harmonics. So the 2 here is stuck to the y of omega hat. And finally, there's regular scalar spherical harmonics, YLM complex conjugate, of the pulsar direction p hat. I think I'll write down the formula for the ALs here, and then I'll push this up to the top. So AL here is 4 pi times minus 1 to the L divided by the square root of L plus 2, L plus 1, L minus 1. And you'll notice that the denominator here would blow up if L was 0 or 1, but fortunately, the sum starts at L equals 2, so you avoid that. And you might feel a bit sick in the stomach thinking, okay, what are these spin weight 2 harmonics? Actually, I think many people who do numerical relativity, and some probably who do just traditional waveform analysis, actually know these harmonics very well. I didn't, but it turns out you don't need to. There's actually only one thing you need to know, which is that they're a complete set, just like the regular spherical harmonics are, for the purposes of this lecture. Okay, so this form allows us to actually evaluate that integral mu mu in a very nice way. Okay, before I go on, questions. Everybody's very quiet today. Yeah, go ahead.
Where's Claude symmetry?
Very good question. I'll come to that. By the way, in the reading materials, there's a frequently asked questions paper that Joe Romano and I wrote. And this is one of those questions, because it gets asked a lot. And the short answer is, the pulsar timing array, its antenna pattern isn't symmetric, right? A source, let's say near the lobe, isn't the same as a source 180 degrees away. It doesn't respond the same way. So that's fundamentally what's behind it. You'll see that in the short wavelength approximation, it does become symmetric. So you'll see that in a few minutes, okay? There are other questions? Yeah.
The directions that you choose for PA and PB, are they like general directions?
It's a good question. It's not obvious that the integral at the top there is invariant under rotations of PA and PB, but it is, okay? I think I'm not going to go through the argument now. I just don't have the time. It's also in this frequently asked questions paper, okay, if you want to see it. So I just have to ask you, take it on trust, okay, that it is actually true, okay? And that's something I've checked carefully, and other people have as well. Okay, yeah?
You said short wavelength, it's probably long wavelength approximation where it becomes symmetric.
You are absolutely right. Thank you. Pardon me. I meant the short arm detector. Yes. Yes. Okay. Yeah.
Is there any way of intuitively understanding why two pulsars having a 50-degree angle in them have zero correlation?
It's not exactly 50 degrees. And remember, this is the expected value. If I pick two pulsars at 50 degrees apart, depending upon where they are in the sky relative to whatever gravitational wave sources they are, they will be correlated some of the time. But if I pick another 50-degree pair over here, they'll be anti-correlated. Another pair over there will be correlated. That one will be anti-correlated. On the average, they're not correlated, okay? This ensemble average is hiding a lot of, there's something hidden in there. Keep thinking back to my example about the expected value of z being 0, even though there's no universe in which z is actually 0, right? A bit like that. Okay. Any other questions before I go on? Yeah.
Would we expect to see a different curve if we use a different ensemble?
That is a very interesting question. I'm going to try and address that a little bit. You're going to see that this curve, it's very difficult not to get that curve. For example, if you just pick a single point source of gravitational waves and you average over all pairs of pulsars at angle gamma on the sky, you'll get that curve. I'll show that actually in a few minutes, okay? That's a good question. Ask it again later if you feel like you haven't heard the answer, okay? Okay, let me, yeah.
On the point of the ensemble average, why don't we ever just take like the absolute value of these things so I can see not just like if the average is going to 0, but there's some.
You know, I should have mentioned this really in the last lecture. Coming back to my example of the scalar field, okay, my canonical simple example, where the universe just contains a single complex number of the form e to the I phi, and the expected value of this is 0. So you might say, well, okay, the expected value is 0, but how can I tell how far off any given universe would be? The answer is the variance. You'd ask yourself, what's the difference between this and that? So this is exactly why the variance is such a useful quantity, because it tells you how far will any given representative universe vary from the mean. And in fact, when I got interested in this topic, the main thing I was studying was what's the variance from this curve in our universe as opposed to this ensemble average. How far away from this curve do we expect to be? And if you look at, I've worked on PTAs for about 3 years, and that was actually the thing that caught my interest, was to try and understand that question of how far do we expect to deviate from this curve? And if I had several more lectures, I would actually talk about that. In fact, I had hoped to, but I just don't have the time. So Okay. All right, if there's any last questions, I take them. Otherwise, let's do some somewhat less nasty calculation. Okay, next one is kind of fun. Let's use this expression to calculate the Hellings-Downs curve again. But this is actually going to be very easy. This is a very beautiful formula, by the way. You should think of this, it's like a propagator. You know, when Matthias looked at the gravitational waves produced by binary systems, he used a propagator, a two-point function, in order to compute the effect of a source over here on the gravitational wave amplitude over there. This is a kind of similar thing. This formula tells you the influence of a gravitational wave source, gravitational wave traveling in a direction omega hat, on a pulsar in a different direction. And this form here, it's a little bit like when you write down the Green's function, for example, for electrostatics, you know, in spherical coordinates. It's a kind of factorized form, or a diagonalized form. It's extremely useful. Okay, let me demonstrate that. So, for example, let's do our calculation of the Hellings-Downs curve using this formula. So what have we got? We've got 1 over 4 pi. We've got an integral d omega. And then we have an f times an f star. I guess I'm going to write it down here. I guess I'll write the other pulsar as q hat right now. Okay, there's no summation over polarizations here because remember that my f is plus I cross. And trust me that if you that the additional term here, the imaginary one, integrates away because it's anti-symmetric under omega goes to a minus omega. So let's just do this. So this is 1 over 4 pi. There's going to be a double sum over L and M, and another double sum over L prime and M prime. I'm not going to write down that L and L prime start from 2 and go to infinity, or the limits on M. Then there's going to be an AL and an AL prime. There's going to be a YLM star of P hat and a YL prime M prime of Q hat. And finally, there's going to be an integral d omega over the sphere of a spin weight 2 harmonic of omega times another one, complex conjugated of omega. I'd be grateful from a thumbs up for somebody that I got all the factors down. Did I forget something? Yeah, these 2's are really nasty. The 2's hang on to the y's on the left. They really mess you up. Thumbs up from someone? Yes, thank you. Okay. You asked for this calculation, now you're getting it. Right. Okay. Now, remember I said you don't need to know anything about spin weight 2 harmonics. If these were scalar harmonics, no 2 here, could somebody tell me what that integral is? It's delta LL prime, delta MM prime. Guess what? The spin weight 2 harmonics are also a complete orthonormal set. Same thing is true. So this immediately simplifies. With single sum, we now have an AL squared okay. I was thinking I'd left something out, but I haven't. Now life gets even easier. Because this sum here, if I do just the sum over M, is a Legendre polynomial. So this becomes the sum L squared. And let's see, Legendre polynomial, if I have L equals 0, each of these is a factor of 1 over root 4 pi. So the answer must be 2L plus 1 over 4 pi. And then we have a Legendre polynomial PL of the cosine of the angle between the two vectors, which in this case would just be P hat dot Q hat. Did I get that right? Okay. But look at what AL squared is. AL squared is 4 pi squared stuff. So this is just the sum, L equals 2 to infinity, of 2L plus 1 over L plus 2, L plus 1, L minus 1, P sub L of the cosine of gamma. Remember, gamma was my angle between P and Q. So this is a really beautiful expression. It's, no, AL squared. Because it's AL squared, the minus 1 to the L falls out. This is bad. So, for people who study microwave background radiation correlation functions and things like this is a very pretty expression. And I seem to have lost a slide. Oh no, I put it there. Okay. What does this sum look like? Well, let's see. P sub 0 is the constant function 1. But of course, it doesn't appear here because the sum starts at L equals 2. P1 is a linear function, goes from minus 1 to 1, but that also doesn't appear here. So P2 is the first function that appears here. That's quadratic. And you notice that the coefficient it appears with is the largest of these, because the numerator here grows like L, but the denominator falls off like L to the 4th pretty quickly. So this sum is already dominated by the first non-zero term, which is P sub 2. And here's a plot. This gray curve here, I got to be careful not to fall off the stairs, is P2. And who was it who asked me about the short arm detector? Somebody asked me what would happen. What's the LIGO equivalent of this? You did, okay. So the answer is, remember LIGO, the short arm case, this factor of 1 plus omega dot p hat canceled, numerator and denominator, and there was just sort of 2 x hats that appeared dotted into the polarization tensor. Carry it through to here, and the sum only includes the L equals 2 term. All the other terms are absent. LIGO has quadrupole response, and then you'll notice, this is the question that you asked me earlier, that the correlation when you flip 180 degrees is exactly the same, because LIGO is symmetric in its response because it's a short arm detector. This is asymmetric because it's a long arm detector. That's the root of the difference. Okay. And in fact, you can calculate, okay, let me stop with that. Right. Okay, how much time have I got? Half an hour. Yeah, I'm going to live dangerously. I'm going to go a little bit fast here, just because I want to, the question came up, and I think I want to try to answer it. So I want to show you that there's another way to get this exact same correlation curve, and it relates to the question that was asked to me a little while ago about what happens if you don't have a Gaussian ensemble. Do you still get the Hellings-Downs curve? And the answer is you do, for an interesting reason. And let me express the idea. Let's suppose that we had a single point source of gravitational waves. So there's just one value of omega hat, right? And the calculation I did here we're averaging over all the omegas. And the reason why is because in the Gaussian ensemble basically contains sources in all directions. But suppose we just asked, what's the response to a single point source? We know, remember the formulas that I wrote down for z, that that just involves this function f. So let's take that function f with one source, one omega hat. We're not going to integrate that. But instead, let's say, suppose we're looking at that one source with many different pulsars. Pulsars here, there, there. And we ask, what's the effect of that single source on all pairs of pulsars separated by angle gamma? In other words, we're going to fix the source to one source, but we're going to average over many pairs of pulsars. That's different than what we've been doing here, where at least mentally thinking about it, that top integral there is saying fix your two pulsars and average over source directions. Pulsar averaging. So what do I mean by that? I mean, let's take the quantity f of omega p hat times f star of omega q hat. I'm going to put averaging symbols over this, but this does not mean the ensemble average that I've been using earlier. This is now going to say average over pulsars. And I'm going to just write here average over p and q such that p hat dot q hat equals cos gamma. So the mental picture you should have is that there's a sphere of directions. This is the directions of pulsars on the sky. We're going to let p vary over the entire sphere uniformly. And for any given p, let's say that one, we're going to take all the q's that lie in a cone of angle gamma around that. That's the picture. And let me write down a formula just because I like formulas. Suppose f is some function of pulsar positions p and q. Then what I mean by this pulsar average, I'm just going to write pq in gamma. That's my shorthand for this kind of wordy thing that I explained over there. Just to remind you, that's what I mean. This is actually 1 over 8 pi squared, an integral dp hat, that's over the sphere, an integral dq hat, that's also over the sphere, a delta function of p hat dot q hat minus cos gamma. That's to enforce the constraint that you're on the cone of whatever this function f of p hat and q hat is. And whenever I look at this, I think, why isn't that 1 over 16 pi squared, right? Because it's sort of 1 over 4 pi twice. But trust me that this factor is correct. If you do the pulsar averaging of the number 1, you'll get out 1. OK, so let's do that in this case. What we're going to be asking is the question, if we have a single point source in direction omega, and we average over all pairs of pulsars on the sky, what do we find? And by the way, this is very relevant, I should just say, because, for example, if you look at, here's data from a paper published by the Nanograv collaboration in 2023. This is reconstructing the Hellings-Downs curve. So with this 3/2 factor of normalization, so it goes to a half, they're trying to show that they find this result. And you notice that there's points here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. There's 15 angular bins. Each of these 15 angular bins contains pairs of pulsars. So they're observing here 67 pulsars. And with 67 pulsars, you can form 67 times 66 divided by 2. That's 2,211 different pairs of pulsars. And so what they've done is they've taken those 2,211 pairs of pulsars, they've divided that by 15, and you get about 147 pairs per bin. They took the 147 pairs that were separated by the smallest angle. That's that point. So that one point represents the average correlation of 147 different pairs of pulsars. In case you're wondering, this bar here does not represent the range of those 147 pairs. If you could plot the range, it would be much broader, and they're not actually averaging the correlation, they're averaging something else. These bars represent the uncertainty in that estimate. That's all. So, in fact, and this is the next 147 pairs at a somewhat larger angular separation. So this process that I'm describing of averaging overall pulsar pairs is actually what's done observationally. So it's not just a mathematical exercise, it's very directly related to what's done experimentally. Okay, so let's do this, because it turns out it's actually pretty easy. So it's almost the same calculation that we did before.
Quick question.
Yes?
So in reality, that integral would have another term there, because if you draw a cone around some known pulsar, it's not necessary that you'll find a pulsar everywhere.
Of course, of course. So the integral here, this pulsar averaging, that's a mathematical idealization to try and reproduce what's being done experimentally. And in fact, the pulsars tend to be more distributed towards the center of our galaxy, and actually antipodal to that, there's not so many off the plane of the galaxy. It still turns out to be pretty good. Okay. Are there other questions? Yeah.
Just to follow up to that, are there like some functions that are thrown into the integral to kind of account for what you just said? Or do we always just look at like an idealization?
So I've calculated the correlation for several different types of ensembles. I've never found anything different than Hellings-Downs. So it seems to be universal. And this is kind of meant to motivate that, the calculation I'm going to do. Okay. All right. So let's just do this. So we're going to do the pulsar average of f of omega p hat f of omega q hat. I'm going to use this funny notation p, q, and gamma to indicate I'm doing the average defined here to the left. And I left my complex conjugate out here, which is important, so that we get plus, 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 cross, cross. Okay. And so let's just write this down. So there's again going to be a sum over L and M and L prime and M prime. There's going to be an AL and an AL prime. There's going to be the spin 2 weighted harmonic of the gravitational wave direction. Remember that we're keeping the gravitational wave direction omega now fixed. We're assuming there's one source. Then there's the complex conjugate of that same quantity. And finally, there's the pulsar average now of y star Lm of p hat y L prime M prime of q hat averaged over all pairs p and q on the sphere at angle gamma. I can hear somebody, is there a mistake on the board? Thank you. Thank you very much. I told you that these things cause trouble. They really do. Subscripts that precede instead of follow symbols should be outlawed. Good. Okay, anything else wrong there? So it turns out to be easy to work out this average. Apparently, this is a standard thing in CMB. I think you said you can find it in Jackson, right? Yeah. Anyway, I had to do it myself. I'm not going to do it now. I'm going to ask you to trust me that this gives you 2L plus 1 over 4 pi times delta LL prime delta MM prime times the Legendre polynomial PL of cos gamma. Did I get it right, Teja? Yeah, put L and M equals 0, right? To check. Okay. So let's see. I'm just going to carry that to the next line. So now, when we do the sum over L prime and M prime, this all collapses to a single sum. And it turns out, oops, that should be an L and M here. And it turns out that this quantity here is independent of L and M. It's just 1 over 4 pi. And so this sum, oh, and I left out something very important. I left out the PL of cos gamma. And so this sum, when you do it now, just turns into exactly the same thing that we have up here. We get exactly the sum of 2L plus 1 over L plus 2, L plus 1, L minus 1, PL of cos gamma. Oh, by the way, I should say you get 1 over 4 pi if L is 2 or larger. The spin 2 harmonics are actually, they don't exist. They're not defined for smaller L's. OK. So what this shows you is it shows you that even if you have a single source of gravitational waves, just one, but you observe it with many different pulsars, if you average over all pairs of pulsars separated by the same angle, you'll recover exactly the same curve. Are you satisfied with the calculation? You seem to know about these harmonics. So.
Yeah.
Yeah, OK.
But I'm a bit surprised that the discreteness of, because this is the ultimate discrete case of one gravitational source, it doesn't manifest itself in the Hellings-Downs curve.
There's a lot of symmetry here, though. You've got one source, right? But you're averaging over all pairs of pulsars. So actually, in this frequently asked questions paper that Joe Romano and I wrote, we actually show by geometrical argument that that's equivalent to fixing your pair of pulsars and averaging over all the sources. So you see, the fact that you've just got one source, if you look at it, let's say, with all possible pairs of pulsars, with all possible orientations, that sort of averages away the effects. OK. If there aren't other questions, there's one last thing I want to do to wrap up these lectures. Yeah.
It seems almost like a tautology to me. Because, I mean, without doing this calculation, I can observe this because there's no special direction.
Yeah, you know, it is. Yeah, maybe you're right, Teja. Maybe you're right. Having said that, many people are confused about this. For example, they'll say, oh, well, the Hellings-Downs is a sign of an isotropic background. And if it's not isotropic, we shouldn't expect that. But that's completely wrong. If you make a gravitational wave background that's as anisotropic as you possibly can, one point source, as long as you observe it with enough pulsars, you'll see this curve. Anyway, I'm happy it's obvious. I've done my job very well as a lecturer.
I think maybe observers don't see it that way because they're aware of how anisotropic the PTA itself is.
OK. I think there's one last thing I'd like to do. I wanted to try and connect this a bit with the Neiman-Pearson thing. So I'm going to put this Hellings-Downs down for now. I'm trying to think if I had anything else I wanted to show you along those lines. If I'd had more time, I was going to talk about this. This is various reconstructions of the Hellings-Downs curve done by different pulsar timing collaborations. We already talked about this nanograv one. This is the Parkes pulsar timing array, the European pulsar timing array, the Chinese pulsar timing array, and the Meerkat Radio Observatory timing array. I probably didn't get that acronym right, but I think I don't have time for that. I'm gonna skip that and hope that one of the later speakers addresses that. Okay. So, very last thing I want to do, I just want to talk about the data analysis problem here. And it's very similar to the ones that are being discussed, but not quite the same. And I just thought I would show what an optimal statistic is in this case and discuss a little bit how that differs from what's actually being used in practice. I've got 15 minutes, which I think is about enough time to do this. So let me do my best. Okay. So I want to make a toy problem in the following way. To help you understand this. So what pulsar timing arrays do is they look at the data from their many different pulsars and they ask, is this consistent with a pattern of correlations described by this Hellings-Downs curve, plus noise in the pulsars, which is uncorrelated between the different pulsars? Or is this consistent with no correlations apart from the autocorrelations pulsars with themselves? So those are their two hypotheses. And here's a toy problem just to help understand how this works. So I want you to imagine that your pulsar timing array is observing data from many pulsars over a period of decades. And so the redshifts or timing residuals, what do they look like? They look like some noisy kind of plot like this. And the PTAs, the expected gravitational wave sources, are strongest at lowest frequencies. So imagine that what the PTA does is it says, okay, I'm going to take this data, these timing residuals or redshift, and I'm going to write it as a sum of a sine term and a cosine term. Fourier analysis. You're just going to drop everything but the lowest frequency mode. And so that pulsar's data is going to become a single complex number. That's it. So each pulsar, you can think of those as the amplitudes of the sine and cosine terms, or the amplitude of e to the I, 2 pi little t over big T, where big T is this interval of time of many years. So ZA, which was a time series, is now going to become one complex number. So the entire PTA's data set, if they have 67 pulsars, has been reduced to 67 complex numbers that are the amplitude of the lowest frequency mode in their data. Everybody with me so far? Okay. So the data, think of it as a column vector, Z1, Z2, up to Z, I'm going to write n sub p here for number of pulsars. That's it. That's your data. And the model of the noise is that this data, z, the data from the jth pulsar, it's the sum of two terms. One is noise. I call that n sub j. I'll try to keep the counting things like this n capital, not lowercase, plus a gravitational wave contribution that I'll call hj. And the idea is now, this is our simple toy data analysis model, is that the noise from the pulsars, let me write it as the expected value of, by the way, all of these things, so we can make column vectors out of all of these, right? So there's a column vector of z, there's a column vector of n, and there's a column vector of h, all complex numbers. And the idea is that the covariance of n dagger, I'm going to write that as capital N. That's the noise covariance matrix. And this is going to be assumed to be diagonal. The reason it's diagonal is because each one of these pulsars is assumed to be an independent clock, and whatever is making fluctuations in its spin or in the arrival times of the pulses is independent of what's happening in the other pulsars. So diagonal here means that there's no correlation between the noise fluctuations from different pulsars. But what about this h? That is going to be described exactly by this function that we've been calculating. That is to say, we expect there's going to be a correlation between the measurements coming from the different pulsars because if there's a gravitational wave background, it's going to produce that. And maybe I didn't stress it before, but I guess since I've pulled down the correct blackboards and I can easily point to it, look at what this coefficient is here. That's the coefficient of the correlation between pulsars A and B or J1 and J2 in this notation. This quantity here is just 1/4 of this quantity HAB that I'd calculated originally. This is just some measured of the squared overall gravitational wave strain. So the idea is that the pattern here is not diagonal. I'm going to call this here, let me write it like this. How do I write this? Let me write it like this. This is a little bit sloppy, but give me some leeway here. I'm just going to write this as h squared times 1 plus delta AB mu sub u of gamma AB. That's a little bit coded, but what I mean is, any given row and column of this matrix here corresponds to two pulsars. If those pulsars are the same, meaning that we're on the diagonal here, we double this from that factor. And then you just use one of these formulas I've written down to calculate what the value of mu is for that particular angle. So this is defined as symmetric matrix whose values are this Hellings-Downs curve, but doubled along the diagonal. Everybody see that? Okay. So from the point of view of data analysis now, what does that mean about z? Well, let's first consider the case where we do have the gravitational wave background present. So then the covariance, ZZ dagger, what is that? That's the covariance of n plus h with itself. There's 4 terms here. One of the terms is the covariance of the pulsar noise with itself. And we've written that down already here, and that's called capital N. Then there's a term which is the covariance of the gravitational wave perturbations with the pulsar noise. But we're going to assume that these things are completely uncorrelated with one another. Whatever's producing the noise in the pulsar spin is unrelated to gravitational waves. So the two cross terms give us 0. And finally, we have this term that comes from the gravitational waves, the Hellings-Downs term. I think I'm just going to write that as gamma AB, as gamma. So gamma is going to be the gravitational wave amplitude squared, this doubling factor along the diagonal, and then the Hellings-Downs function at the angle it separates the two pulsars. Okay. I think I'm happy with that. Any questions so far? Okay. So let's use Neyman-Pearson, the Neyman-Pearson lemma. So we need to write down two hypotheses here, our null hypothesis, no gravitational waves, and our signal hypothesis, gravitational waves. Now the interesting thing is this is not what PTAs do. Their null hypothesis is different than what I just said. So let me try and explain what it is. First of all, what's the signal hypothesis? I'm going to call that H sub s. Well, the signal hypothesis is that Z is drawn from a normal distribution. Uh-oh, I've got too many n's here. Let me try and make some kind of curly n. That means a normal distribution. Yeah.
That the y for the a should be Neyman.
That's right. Spelling is not my strong point. Okay, and in fact, neither are weird curly symbols. Let's trust that you guys know what a normal distribution is. You recognize that that's what I mean by n here. So the Neyman-Pearson lemma, the signal hypothesis is that this number z is drawn from a distribution with this of 0 mean, but with the covariance matrix, let me call it C, which is equal to n plus gamma. It has off-diagonal terms. The noise hypothesis, or maybe I should say the null hypothesis in the case of PTAs, you might think would be that Z is drawn from a normal distribution whose covariance just has that n term. But actually, that's not what they do. When they estimate these different covariance matrices from the data, what they do is they pick as their null hypothesis that Z is drawn from a normal distribution where they take here the diagonal part of C. That is to say, it's as if you had gravitational waves that cause a common diagonal term, a common correlated Earth and pulsar term in every pulsar, but somehow magically these Hellings-Downs correlations weren't there. That's the null hypothesis. They call that common uncorrelated red noise. The uncorrelated red noise is a reference to the fact that they've kept the diagonal terms and just dropped the off-diagonal ones. And so now we can do exactly the machinery that Barak laid out. And I was going to actually prove the Neyman-Pearson hypothesis, but Barak's proof is better than mine. That was the guy who goes into the room with a backpack, and his goal is to carry out as many coins as he can, or as much value as he can. So you start with the highest value per unit weight coins, you stuff those into your backpack, and you keep going until you've filled the backpack. That's your threshold. So here, the Neyman-Pearson hypothesis is now going to be the ratio of the probability distributions associated with these two different hypotheses. So this one, because I have complex data, this probability distribution is 1 over the determinant of, I better write bigger, This probability distribution in the numerator is 1 over the determinant of pi times that covariance matrix times the exponential of minus z dagger C inverse z. If you're wondering about the missing factors of 1/2 here and 2 there, it's because this is a complex variable z, not a real one. Yeah.
Are there 3 parameters in this covariance?
Can I pretend that the answer is no, because otherwise you're going to mess me up with having to go easy on me. It's the last lecture and the last day, and actually the last minutes. Let's pretend this is simple hypotheses. All right, and in the denominator here, we have instead the determinant of pi times the diagonal part of c, and then the exponential of minus c dagger times the diagonal part of c inverted times z. And so this means that if you take the log of this, and you don't worry about the fact that there's constants in here, your decision rule about whether you've detected a gravitational wave background or not, up to an unimportant constant. I guess it's not so important if all you can carry is 30 kilos, but anyway, up to a constant which isn't important for this discussion, is just z dagger times, sorry, plus z dagger times the diagonal part of c inverted minus c inverted times z. And I'll just point out that pulsar timing arrays are, in fact, computing an optimal statistic, which is not actually optimal, because it's not this. They've instead chosen something which is robust. It's similar to this, but they've set it to 0 on the diagonal to eliminate uncertainties associated with misestimating pulsar noise. Anyway, I see that I've run out of time. I was hoping to go a bit more into details about this, but I think it's time for lunch. Anyway, you've been a great audience. Thank you very much. And if you have other questions, come and ask me.